Good day, everyone. This topic is about the use of artificial neural network in developing model for bond strength. The paper was published in the International Journal of Geomate, and my name is Nolan Concha, a faculty from FEU Institute of Technology, and I'm here to present a topic on bond strength model of corroded reinforcement in concrete using neural network. Corrosion of rebars is an electrochemical process. It involves the movement of charges by converting the iron into iron oxides and hydroxides. Generally, corrosion of steel in concrete is composed of two types. The first one is what we call the chloride-induced corrosion. Chloride-induced corrosion is also called local corrosion. It damages a film without changing the electrochemical environment of the surrounding concrete. In this process, the chloride ions find its way in the concrete and gradually reach a certain critical concentration that they will cause damage in the passivating film, exposing the rebar to corrosion. On the other hand, the carbonation-induced corrosion is what we call general corrosion. In this process, there is a change in the electrochemical environment of the enveloping concrete. The film becomes thermodynamically unstable due to the ingress of carbon dioxide through pores and reacts with calcium hydroxide in the concrete. Corrosion of steel reinforcements due to chloride environments is regarded as one vital structural health concerns in concrete structures. Embedded rebars at this rusting stage expand and develop radial stresses in concrete, resulting to cracking, bulging, and spalling of concrete as shown in this figure. Corrosion also results to the buckling, snapping, and ineffective bond characteristics of reinforcements due to continued reduction in the effective bar size of the steel. When subjected to reinforcement corrosion, concrete structures experience delamination, in which the oxidized metal requires greater space causing wedge-like stress. Separation of concrete and reinforcing steel bars occur when the force due to the stress surpasses the relatively weak tensile strength of concrete. Surface and internal cracks tend to develop in concrete and promote exposure of reinforcements to corrosion. This, in turn, imparts an excessive reduction in the bond strength, characterized by the adhesion and slippage resistance between steel and the enveloping concrete. With all these effects, this in turn may reduce the serviceability and durability of the structure. The bond stress, in particular, balances the internal stress in the rebar through composite action of steel and concrete. When sufficient bond develop, when sufficient bond is developed, the rebar will not be pulled off from embedment and the reinforcement will reach the desired yield strength for ductile design. This controls the structural behavior of concrete under static and dynamic loadings. However, when the embedded rebar begins to oxidize, the effective bar size decreases and the adhesion of the steel-concrete interface starts to deteriorate. Lugs and ribs of the rebar will be continued through continuous corrosion, resulting to the dissipation of the wedging action at the contacting surfaces. In turn, at a certain critical level of corrosion in steel, the bond will be reduced significantly, causing the bar to slip from the enveloping concrete. With these undesirable effects of corrosion, it is therefore essential to develop a model of predicting the bond of corroded steel reinforcement in concrete. However, in developing bond model is not an easy task. As you can see in this figure, the free body diagram of a bar, the bond stress mu is assumed to be acting uniform all throughout the length of the bar. However, in actual conditions, the distribution of the stress all throughout the length is not uniform. A large number of variables affects the bond strength, such as the embedment, the compressive strength, the rebar size, the quality of concrete, and many other factors which are not included in the prediction of existing bond strength models. Further, aside from large number of variables involved in the development of the bond, the interactions of these variables also involve non-linear complex interactions. The question now is there a tool that can be used to reasonably model the bond strength considering the complexities? Artificial neural network is one essential and convenient way of developing models of highly complicated nonlinear relationships. It can be used to model noisy data. It can also be used in dealing with complex relationships between variables, and it can also develop model involving multiple number of variables. Due to its profound adaptability to derive outputs from complex or inaccurate data, researchers find this method very useful in providing projections to new situations of interest. ANN is an information processing algorithm adapting the way a biological nervous system like brain synthesizes a certain set of information. The main component of this model is a novel structure of the information processing scheme. It is made up of a large network of highly interconnected processing components considered as neurons, which work as one to address specific problems. Like biological human being, ANN learn through a set of observation. An ANN is arranged for a specific application like classification of data or recognition of pattern by means of learning procedure. With these desirable characteristics of ANN, it is plausible to develop a bond strength model given the complexities of the physical system. Therefore, in this study, a novel prediction model of bond strength of corroded reinforcing steel bars in reinforced concrete using artificial neural network was carried out. Through the inspection by means of laboratory and field testing, inputs in the model can be collected and be used to predict the bond strength of the reinforcement. The output of the model can be used to perform possible predictions of bond loss that can be utilized as baseline information for sustainable design. It can also be used to assess structural component safety condition to derive at a proper diagnosis and effective preventive measures to prolong the service life of concrete structures. The output can be further used as one component in assessing the reliability of the structure. As shown in this slide, the study composed of three major methodologies. You have the experiment, the data collection, and the ANN simulation. The desired band model will be a function of 8 independent variables, and these are the embedment length, rebar diameter, concrete cover, the compressive and tensile strength of concrete, which will come from the UTM test, ultrasonic pulse velocity, which will represent the quality of concrete using the UPV test, crack width due to rebar corrosion. After subjecting it to accelerated corrosion, the crack openings will be measured, and the mass loss. After performing the various tests in all the samples, this table shows the descriptive statistics of the set of collected data, such as the mean, the standard deviation, the coefficient of variance, minimum and maximum values. The minimum and maximum values of bond strengths were recorded as 0.872 and 16.481 megapascals respectively. The bond strength results obtained from a short-term pull-out test of 100 samples was used in the development of the model. 70% of the data pairs were used in training phase of the model, and the 30% was used in the testing phase. Basically, the development of ANN model have three interconnected layers as shown in this figure. The first one consists of input neurons, and in this study consisting of 8 neurons, which then send the data to the second layer, called the hidden layer, which in turn send the information to the next layer, considered as the output neuron. In this study, the output is the bond strength of the reinforcement. Each neuron performs a weighted sum of inputs from neurons connecting to it during the process, and we call it the activation process. The simulation ends when the entirety of information sources surpasses some already set threshold value. In the development of the model, the learning algorithm used was the feed-forward backpropagation. The hyperbolic tangent sigmoid function was employed as neural activation function, which returns values between -1 to 1 in the output layer. The input layer of the neural network model is composed of 8 distinct individual nodes. Each node represents the predictors in the model, which includes the compressive strength, tensile strength, embedment length, rebar diameter, concrete cover, ultrasonic pulse velocity, corrosion level, and crack width of the concrete. One hidden layer was used in the model, and the number of hidden nodes was varied between 5 to 8. Nodes were varied in the hidden layer to explore a simple and suitable neural network architecture that will provide better prediction results. The output layer was composed of one node representing the bond strength model, and an error tolerance of 0.001 and maximum cycles of 100,000 were used as threshold criteria to cease the simulation process. Early stopping, validation phase in the development of the model, and few members or numbers of hidden nodes were considered to minimize the chance of overfitting and enhance the generalization of the model. Neural network model structure having 8 input nodes, 5 hidden layer neurons, and a single node in the output layer was denoted as N851. In selecting the best performing ANN architecture among the variations considered, the mean squared error and the correlation coefficient R were used as performance metrics. The model having the least MSE and closest R value to 1.0 will emerge the best ANN model. The result of the simulations of the 4 ANN models with the corresponding MSE and R as shown in this table. Apparently, the neural network having 8 nodes in the hidden layer provided the most desirable performance indicators. The N881 model exhibited the least band strength prediction errors and in good agreement with experimental results. The model was able to achieve learning, considering multiple predictors and fuzziness in the introduced data pairs. The MSE and R of the derived model were 2.967 and 0.954 respectively. In contrast, the N851 model having 5 hidden nodes was the least performing model. The next question is the proposed ANN model provide satisfactory prediction results? The error distribution obtained from simulation of training and test datasets is presented in this figure. It is evident that majority of the predicted bond strength provided marginal errors against experimental results. About 61% and 57% of data from training and test sets, respectively, were within the positive and negative 10% error. Though there were few misfits of roughly 16% providing more than 25% predictions, the model was able to perform well in training and testing phases of the simulation. The experimental and predicted values of the model for training and testing phases were also plotted in the second figure. The model was able to perform better in the testing phase, giving an R value of 0.959 and an average error of 14.94%. The R value and average error in the training phase of the model were 0.945 and 14.19% respectively. A vast majority of the samples with overall R equal to 0.957 exhibited a close fit from the 45-degree line, showing desirable agreement between the predicted and experimental results. An average value of experimental and predicted values of 0.976 further demonstrates robust performance of N881 model in prediction of band strength. Using 95% significance level in the analysis of variance tests conducted between predicted and experimental band strength values, it was found out that the critical value from a statistic is 3.885. The value is relatively higher than the calculated F of 0.118, suggesting that no significant difference is observed and the values are statistically the same. Various band prediction models available in the literature were considered and compared to the performance of the proposed N881 model. 8 band strength values from experimental data were not used in the calibration of the model. This dataset was used to test the band performance of the proposed ANN model against the developed models by Cabrera in 1996, Lee in 2002, Yalciner in 2008, Chung in 2008, Hu in 2017, and the developed regression equation. The experimental and predicted results of the various values were plotted in the figure shown. The scatter plot diagram was so dispersed, demonstrating a large number of deviations of the points from the 45-degree line. The models developed by Cabrera, Hu, Chung gave an overestimated values of the band strength due to the limitations of the variables considered. Most of the proposed models provided significant errors in the prediction results. This can be attributed to the inability of the models to capture significant band reduction in the presence of internal and surface cracks in the concrete. The proposed N881 model, on the other hand, was able to exhibit robustness in predicting band strength values, as shown in this figure. A close fit can be seen from the graph with an R value of 0.986. The limitation of the hidden nodes and the early stopping adopted in the development of the model worked so well to improve the generalization of the model. The average observed error in the prediction results was 17.22%, with maximum and minimum errors of 53 and 0.78% respectively. Each parameter was varied in isolation to the other variables to understand its effect on the band strength of concrete with corroded reinforcement. The band behavior was also investigated for samples having different compressive strengths. It is evident in the first figure that larger CC over D ratio offers better confinement and higher band strength. The crack resistance was improved due to larger concrete cover enveloping the reinforcement. The radial stress due to expansion of corrosion products was effectively resisted by the increasing cover, offering better adhesion of steel in concrete. It is evident as well in the second figure that the band strength is better in concrete with higher UPV. It is clear that at low values of UPV, which was associated with the immense corrosion level and severe crack formations, The bond strength was excessively low for all compressive strength of concrete. At higher values of UPV, on the other hand, the cracks and amount of corrosion were less, and thus relatively more resistant against slipping of reinforcement. At an early stage of corrosion, the bond strength is increasing but deteriorates thereafter in the first figure. Increasing bond strength were observed for 21 megapascals with corrosion up to 1.08%, while 0.54% for 28 and 35 megapascals. These amounts of corrosion products were sufficiently enough to expand freely through permeable structure of concrete and occupy the pore spaces. The 21 megapascal concrete samples accommodated the largest volumetric expansion of the rebar because of the volume of capillary voids in the concrete was relatively greater. Beyond these amounts of corrosion, however, the bond strength decayed continuously for all compressive strengths. In the next figure, the large crack openings significantly reduced the bond strength. This growing crack width was associated with the rising internal tensile stress due to excessive corrosion level in the reinforcement. As a result, wide openings were created, exposing the rebar to chloride-rich environments, allowing corrosion to develop in a more rapid phase. Upon careful analysis of the results, the following conclusions can be drawn in this study. The first one is the neural network model N881 having 8 input nodes, 8 nodes in the hidden layer, and 1 output variable provided the best prediction performance among the various ANN topologies considered. The second is the proposed N881 model provided the best prediction results relative to existing band strength models. The proposed model provided the least mean squared error and the highest Pearson correlation coefficient, indicating robustness in the prediction or predicting the band strength of corroded reinforcement in concrete. And finally, the ANN modeling can be used to develop a robust band strength prediction model, even with the presence of noisy, complex, and multivariable data. The neural network was able to provide satisfactory prediction model. That concludes my presentation. Thank you everyone for your kind attention.